massive spring. Usually we solve a spring problem by assuming that the spring is massless, and we get that the oscillation frequency is the square root of k over m. And if you forgot, that's from Hooke's law, you get a differential equation, and this is the solution, right? It's a sinusoidal, it's a second order differential equation, the solution is sinusoidal, the frequency is square root of k over m. Right, now I want to think about the case where we have a spring with a mass at the end of it, but now the mass of the spring is non-zero. It's given by capital M. So the first thing we want to do in this problem is to write down the kinetic energy of this system. So the kinetic energy of the entire system, I'll denote by the letter T, is equal to 1/2 m x naught, I'll explain that in a moment, x naught dot squared plus 1/2, wait a second, I don't know what to write here, as a matter of fact. So this term is pretty clearly, if I call this displacement x naught, that's the displacement of the mass at the end of the spring, and I tell you that a dot over a letter denotes a derivative of that variable with respect to time, then this is clearly the velocity of the mass at the end of the spring, and this is clearly the classical kinetic energy of the mass at the end of the spring. It's 1/2 mv squared. So this is the kinetic energy of this part, but now we have this whole spring, which is massive, which must have some kinetic energy associated with it since it's moving. And I don't know what that is, so I'm going to put like a box here and just say question mark. We have to express the kinetic energy of the spring itself. So the first thing here is, like most problems in physics, we're going to divide it up into a lot of little tiny pieces. So we're going to talk about the spring as though it were composed of infinitely many tiny particles, each of mass dm, right, our infinitesimal mass element of the spring. And we're going to ask, what's the kinetic energy of the entire thing, right? So let's just try it. So it's T equals, so just to be clear, this is T sub s, and that means the kinetic energy of the spring equals 1/2, like usual, dm. So we're talking about an element of kinetic energy, so I'll call it dt sub s, 1/2 dm times the velocity of a spring element squared. So this is all fine because we have the total mass of the spring. Dm is really just lambda dx, where lambda is the linear mass density equal to capital M over L, if L is the length of the spring. Let me just say that L is the length of the spring. So L is the length of our spring, and we can think about this as sort of like an x-axis. Then the linear mass density is capital M over L, total mass over total length. So that takes care of our dm. All right, it's just m over L dx. But this term here, the velocity of a spring element, is a bit more tricky. And to solve for that term, we're going to make the following assumption. So I'm going to say, assume the spring is homogeneous. So what that means is that there is nothing about one piece of the spring to differentiate that piece from any other piece of the spring. The only thing that differentiates one piece from another piece is its position along the x-axis, and that's just obvious because they can't all be located in the same spot. So other than that, they're all the same. They all have the same mass. That's to say the mass is distributed evenly throughout the spring, and there's nothing to differentiate one element from the other. So what do we know about the motion of this spring? What we do know is from our previous problem of the massless spring, right? This is our massless spring, if you recall. From our previous problem, we know that the motion of a massless spring is, right, x of t equals some sinusoidal function. I'm just going to say cosine of omega t, right? So usually there's an amplitude here, or phase factor. We're setting that all equal to 1s and 0s. So now that's our previous problem of the massless spring. So let me make a line here just to make it very clear that that's not what we're dealing with now, but it's going to be helpful. So in this case, we have our mass at the end of the spring, and it's going to be oscillating sinusoidally. Moreover, the entire spring is going to be oscillating sinusoidally. So we know that this, right, this x naught as a function of time, x naught of t is equal to, again, I'm just going to say it's equal to cosine of omega t, which means that x naught dot of t, that's the velocity of the mass at the end of the spring, is equal to negative omega sine omega t. Okay? So we know that this is the motion of the endpoint. What about the motion of the fixed point? Well, it's 0, right, because it's fixed. So what about the motion of the points in between? Since the spring is homogeneous, the motion of the points in between scales linearly up to the motion of the endpoint. And what that means is that if I write the position as a function of time of a point in between, I'll call it x of t, is going to equal x, this is the position along the x-axis, over L, that's the total length of the spring, times the motion of the point at the end of the spring. So times x naught of t, which is cosine of omega t. So what I've done here is I've made it so that when we're at position L, when we're at the end of the spring, it's moving just like it should be moving, cosine of omega t. When we're at position 0, when we're fixed here, it's moving not at all, or it's at x over L is 0 over L is 0. And when we're at some place in between, it's moving somehow in between. So this is our position as a function of time of an infinitesimal element on the spring. Implies that the velocity as a function of time of our infinitesimal element along the spring is minus omega x over L times the sine of omega t, right? But this is exactly what we wanted here. This v sub s was supposed to be a velocity of a point along the spring. So now we can just plug into our expression for the potential, for the kinetic energy of the spring motion. And I'm going to substitute here dm, I'm going to substitute lambda dx, which is m over L dx. So dt sub s, this is an element of kinetic energy for the spring, is equal to 1/2 dm, which is m over L dx, m over L dx, times the square of the velocity of a spring element. But this is the velocity of the spring element, so we have to square it. The negative goes to positive. We get omega squared x squared over L squared times the sine of omega t squared. Okay? Oh, I'm off the screen. But there you see it, right? So now, to solve for the full kinetic energy of the spring, we just have to integrate this whole thing, right? And we're integrating dx. All we have here is an x squared. Everything else is constant, right? Inspect every term here. There's no x anywhere except for right there. So that all comes out of the integral. So we get that the total kinetic energy, so T equals, and the integral runs from 0 to L. It's along the whole length of the spring. So it equals 1/2 capital M over L cubed. I'm just rewriting all the constants outside of the integral, times omega squared, times the sine of omega t squared. Now we have the integral from 0 to L of x squared. Well, the integral of x squared is just x cubed over 3, and if we evaluate it at 0, we get 0, so that's negative 0. And if we evaluate it at L, we have L cubed over 3, so I'm just going to write times L cubed over 3. Right, and that's our full kinetic energy. Obviously the L's cancel, and we have a simpler statement, which is that it's m over 6 omega squared sine squared omega t, right? That's the kinetic energy of the spring itself, of the entire spring. Now, does this look familiar? We have omega squared sine squared omega t. But remember that when we were talking about the motion of the mass at the end, we had a velocity of that motion given by omega sine omega t. So the square of this is clearly omega squared sine squared omega t. So we can actually rewrite the kinetic energy. Now I'm going to move to a new page. But we can rewrite our kinetic energy here as just m/6 times the square of the velocity of the mass at the end of the spring. So the spring kinetic energy, right, so T spring, T sub s, equals m/6 times x naught dot squared. So now, what about the total kinetic energy? Let's go back to our total kinetic energy of the entire system. It was 1/2 m x naught dot squared, that was the kinetic energy of this, plus some question mark term, which was supposed to be the kinetic energy of the spring. But we just found the kinetic energy of the spring, so we can now plug in. So we get T equals, right, so total kinetic energy equals 1/2 m, little m, x naught dot squared, plus the kinetic energy of the spring, plus m, big M/6, times x naught dot squared. So what I want to do now is factor out the 1/2. And what I do when I factor out the 1/2, and I'll show you why I'm doing that in a second, but let me just do it. I factor out the 1/2, I get little m plus big M over 3 times x naught dot squared. Right? So that is our full kinetic energy of the system. That's the kinetic energy of the spring plus the kinetic energy of the mass at the end. Now what you'll notice is that this looks just like our old kinetic energy, right? So if we look at the kinetic energy of just our massless spring, right, this thing has kinetic energy 1/2 mv squared, where v is the velocity of the mass at the end. And it had frequency root k over m, right? So what we have here is essentially a kinetic energy with effective mass, right? So this can be like our effective mass, and the effective mass is equal to little m plus big M over 3. So in the old case, for a massless spring, omega equals root k over m. But now, in the new case, for a massive spring, we're going to take our effective mass and plug it in here, and we're going to get omega equals the square root of k over little m plus big M over 3. And that is the solution for the motion of the mass at the end of the spring. It's going to oscillate sinusoidally with this frequency.